Hello and welcome in my series Life in Space, where I made a very long and programmatic video. I will reference it below. I will make shorter videos now and take out single aspects that I may have mentioned or may not have mentioned, but that we can look at a bit more closely. And one such topic are dissipative and conservative structures, more dissipative structures, and self-organization, and some examples for that. One example is here already on the picture, which is a Rayleigh-Benard structure, which is more or less convection in a thick fluid that is heated from below. So there are these cells where the warm soup comes up and colder soup goes down. The overview of today's video: first we will talk about structures and also dissipative structures, then come to life, because the two things are more or less connected, not always, but quite often connected. And then we'll talk about growing structures and about the cell, which is a very complicated structure, and then also look at aggregates of cells and also at aggregates of animals. So if you look at reasonably complex structures like these spirals here, often they are actually simpler than you would expect, or they tend towards something simple, but if you look more closely, they tend to be still more complicated. I could talk a lot about galaxies, for example. Classical galaxy has two arms, but if you look more closer, every galaxy is different. And they can have inner and outer arms, and they can have a beam in the middle and this kind of thing. And it's only coarsely understood what builds these structures. The same here, the spiral structure in the water. Often material tends to flow inward and being swallowed in a spiral structure. So sometimes you can wonder why very different structures look very similar. And this probably has to do with similar processes and similar limiting conditions that build the structures. A problem is that we don't have a proper science that deals with description and prediction of structures. The only thing we have is systems theory, which is good for certain things, for example electronics or things like that. But the description of really complicated structures is still almost impossible. And another important science, of course, is chaos theory, that deals with irregularities. And not all irregularities are undescribable, as we will see in a minute. In the earlier days, people thought that if you have large energies, that's not good for structure building, which is sometimes true. If you throw a bomb, it tends to destroy structures and not to build structures. But the work of Ilya Prigogine, who got the Nobel Prize for it, has shown that sometimes you can build quite impressive structures far from a thermodynamic equilibrium. And he also described mathematically how that can happen. And he dealt a lot with dissipative structures, which is exactly the description for that, for energy flowing through a structure and the structure keeping its form despite energy and even material flowing through. And the best textbook example for this is a candle, because the wax flows through the flame and is being combusted, and the material changes all the time, but the structure of the flame stays basically the same. Or another example is the convection patterns, as the one we have seen on the first slide, and also the ones you see on very good images of the sun. So here cooked material comes up, and once it's cooled down a little bit, it goes down again. And often you can have self-organization. So not always chaos makes order, but also order makes, not always order can turn into chaos, but also chaos can turn into order. But as we learn from thermodynamics, it's always globally the chaos always grows and the order decreases. But locally that's not always the case. So you can have open systems and have order in these open systems, and the energy is going out from the open systems. So often you can find islands of predictability in a sea of unpredictability. And Prigogine also stresses that you have to look at microscopic and macroscopic structures, and sometimes, despite the microscopic structures being chaotic, you can tell regularities in the macroscopic structures. For example, if you have a lot of atoms, they can show some regularities, like for example the gas laws, despite the movement of the single atoms is quite chaotic. You can describe the gas, which is a macroscopic structure, without having exact knowledge of the microscopic structures and functions. He dealt with this kind of things. And he also wanted to apply chaos theory not only to chemistry, but also to complex and even social structures. These were his ideas. I don't think that many people know about Prigogine and his work. I mean, Ilya Prigogine. Then the connection to life is somehow very close. Of course, not all dissipative structures are life, but all life consists of dissipative structures, sometimes connected with conservative parts. For example, if you look at our bodies, each cell is a dissipative structure, but we have a skeleton which is a conservative part. And this has to do with us being multi-celled. That makes everything much more complicated. And we will probably talk about multi-cell life in a later video. Life partly is based on self-organizing systems. And one example for self-organizing systems are membranes, which are very fascinating. You have these fatty chains with a water-soluble group and a water non-soluble group. So as soon as you kick them into the water, you have this bilayer structure, which tends to form the surface of a sphere. And what happens if you take a knife and cut through? It will reorganize in two smaller spheres, which is already what a cell does, more or less, if you duplicate it. Sometimes they grow before duplication and sometimes they grow after duplication, but the duplication is more or less just cut through, and then if you have enough organelles in both parts, two new cells will be built. And this is actually something that happens in humans in pregnancy. If you touch a fertilized egg in the right place, it will just split, and then you have two, which is monozygotic twins. It just takes that, touch them in the right space. Of course, these eggs have a cell skeleton, and this makes it more complicated, but it's possible. And the dividing cell also has a cell skeleton, and it's a highly ordered process. But the fascinating thing is the membrane kind of does the split by itself. It doesn't only fill up holes, it will also split into two smaller entities if you cut somewhere. Maybe symmetric, maybe asymmetric. Depends on the cut. And then there are also structures that grow. Structures that grow in size, and also structures that can duplicate without being alive. And one example shown here are snow crystals. So you have just water molecules, and you have this hexagonal thing to start with, and it grows also hexagonally, and the crystal can also change its form, but it will always stay hexagonal and symmetric. So fascinating stuff. And another example are stalactites. The water is chalky water is going through, and they grow. They grow from the top down and bottom up, and in the end they may touch in the middle. So everything you have is running water and it makes these structures. Then, for example, there are aggregating proteins in cells or around cells, and one example for these are amyloids, which we don't really like, but they're very interesting because you can have them folded in different ways, and if you fold them in an aggregating way, the aggregated protein is a template for the other proteins, and then these aggregates grow and grow and grow. And they can grow, first they will build oligomers, and then they will fall out because they're not soluble anymore. And then they can build fibrils, and they can also build plaques. And it doesn't have to do with the structure of the molecule, but with the structure of the aggregate. So it's quite similar to what happens in the snow crystal. And the other thing again is actually galaxies. We're back at galaxies. They tend to swallow up smaller galaxies and grow. And they will also change their structure by that. And will strip out some stars and some gas from the smaller galaxies, and the smaller galaxies go in and out, and after a while you can't find them anymore. So galaxies used to be much smaller in the beginning and tend to grow. And the cell, of course, as I already mentioned, is a dissipative structure. You have supply coming in, and also energy going out, and it can also reproduce, which here I've shown a cell that has a core, and in these cells it's a lot more complicated than in the prokaryotic cells. And the eukaryotic cell is already a basis for multi-cell life. And it's interesting that we have actually bacteria in the cells, which make the aerobic breathing for us. So we just took their advantage by more or less swallowing them. And there was also a gene transfer, because they have their own genetics, but some of the genes now are in our genome. So the mitochondria, these formerly bacteria, are not able to live without us anymore. So it's a symbiosis by these ones and us. We get their energy and they get our supplies and our organization. But many things are not understood yet. And this is an example of a cell division. And as I already mentioned, the cell can grow first and divide then, or it can divide and grow then. And the interesting thing about the process is the two daughter cells look practically identical, which is of course an example of unsexual multiplication, whereas you can also have a sexual one where genes are exchanged. But if it just splits, the genes are hopefully exactly the same, unless there are some mistakes during the division. And yeah, I made this very short about the single cells. We could talk about this more later, but time is running. And cells can also aggregate, which is an interesting basis for multicell life, because the first multicell structures were just identical cells that aggregated and had some advantage by aggregating. They could do things or profit from each other, and also started communicating with each other. But the ways of communicating were quite simple in the beginning, which is more or less exchanging molecules. And after a while, some of these molecules also had a message in them, so they were, messengers. And here, this paper I read shows how the cells actually anchor in one another's structure. So the distance between the cells is exactly the same. It's more or less like anvil-like structures that grab each other in the part that grows thicker. So this is an example for cell aggregation. And then a second step would be specialization, but these cells don't do that yet. And here are some aggregations of multicell animals, which are very impressive to look at. For example, an ant's hive, where each ant follows relatively simple rules, and there is emergence of what the whole hive is doing beyond what the single ant is doing. The same thing you observe in their nervous systems, where the system does things that the single cell doesn't know it is contributing to. And you can also have, for example, fish building large colonies. And following certain rules. The same thing with birds. For example, one rule is you never stay in the middle. You're in the middle, then you go out, and then you go back into the middle again. And this is kind of a democratic thing, because the ones from the outside, they can be eaten up, for example, especially for the fish. And the ones in the inside are more safer. So if this is exchanged all the time, also the risk is distributed equally. Or in Africa, for example, you can have these large herds of mammals, which are also very impressive, like the buffaloes or the zebras. And also in humans, you can have humans combined in a rather chaotic way, and you can have humans combined in a very orderly way. And sometimes you can see a transition between these two. For example, orderly structures can dissolve. For example, if you have a revolution. But also the inverse thing can happen. I was always amazed on escalators in the railway station. If you look, if there are only few people, they tend to be chaotic. For example, in Zurich, you have to stand on the right side of the escalator and walk on the left side, which doesn't work for most of the day. But in rush hour, when there are many people, the orderly structure builds. You could say maybe it's not the same selection of people, that's possible, but if you look from far away, you would say, oh, it's rush hour, now the structure is building, and as soon as the number of people goes down, it will turn into a chaotic structure again. This kind of thing. Now I'm coming to the last slide, and here I wanted to show, I'm not a big fan of personal cult, but this whole presentation is so strongly connected with Ilya Prigogine that I wanted to show his face. And I also think he didn't get the attention that he actually deserved, partly because the topic he worked on is quite hard to understand, but I tried to explain it. So, thanks a lot for the attention.